Hey guys, so this video is a review for the first exam of Math 141. It's going to cover Chapter 1 and sections 4.2 and 4.4. These first few sections all kind of blend together, so sometimes I'll have more than one section going in a question, so I'll try to kind of note where they came from, so in case you want to go back to it in the homework or the lecture notes, you can find it. So, okay, this first one is a graph with like a bunch of prompts. There's all kinds of stuff we can ask on these. So let me just kind of walk through these. One, find the domain. Okay, so remember, domain is our x values, and we're going to write it interval notation left to right. So right there is as far left as the graph goes, and then right there is as far to the right it goes. So it looks like it's going to be from -9 up to 8. And then find the range, so that's going to be low to high. So it looks like the lowest the graph goes is right here, and it goes all the way up to 6 and includes. And if there's graph there, whether there's a dot there or not, if it's just a smooth line, that counts as included, because this graph, the line is actually an infinite number of dots, so all of these points are included. So that was what, -5 to 6. So the next one is on what interval or intervals is f increasing. So remember, when we're doing increasing, decreasing, constant, we want to do that in terms of it's the interval it's happening on, not it's increasing from -5 up to here. It's increasing from -4 to 0. That's the interval it's increasing on. So these are always going to be x values. And then we always use parentheses because at these endpoints, it's actually right here, technically it's constant for a second. You know, the slope was negative and it's 0 and then it's positive. So we can't really include the endpoint because it's not increasing. It's actually changing direction. So always parentheses. So for increasing, let's see. From it's getting bigger, and increasing is it gets bigger as we travel from left to right. So it'd be increasing right there, and then decreasing for a bit, and then it's going to increase from here to here, and then from here to here again. So let's see, that is from -9 to -7, and then -4 to 0, and then from 4 to 6. And so then decreasing, that's going to be, so where it's going downhill left to right, so that's right here, that's constant, that'll be decreasing. So it looks like from -7 to -4, and then from 6 to 8. And then lastly, on what interval is it constant? So that's right in here where it's flat. So that's from there to there. And so from 0 to 4. What are the x-intercepts? So those we just read right off the graph. So the x-intercepts are at -7, 0, comma, not union, because this is now an ordered pair. This is just that point. And then at -2, 0. And then what else do we have? What's the y-intercept? So it looks like 0, 4. Find f of -3. So now we're doing the function notation stuff. So f of -3 means when x is -3, what's y? So when x is -3, it looks like would be right there, and so y would be -3. Is f of -1 positive or negative? So it's not asking is -1 positive or negative, it's asking if f of -1 is positive or negative. So f of -1 is what the y would be when x is -1, and so that would be 3. So there we would say it's positive. So J is for what values of x does f of x equal -3? Okay, so this means what x's make it come out to y equals negative 3. So if I just draw a line through negative 3, any place it's crossing there is what does that. So this would be at x equals negative 5 and negative 3. And then last one we have, for what values of x is f of x less than 0? So that's going to be, again, think of f of x as y. So where are the y values? Actually, sorry, it was less than or equal to 0. So the y values are less than or equal to 0 if it's below the x-axis. And it could be equal to, so that's going to be from right there all the way to right there. Because on this whole interval, that's where, if you say what's y, it's a negative value or possibly 0. And then that would be from, and those are inclusive because of the equals. So we'll use a bracket, negative 9 to negative 2 with another bracket. Okay, so these are find the domain for each of the following functions, and these are out of 1.2. And so there's basically kind of two things, at least so far, that we have that mess up domain. And one is if I have some math under a radical, then that math needs to be greater than or equal to 0. Because a negative under a radical would make it imaginary, so not in the domain. We wouldn't see it when we graph it on in the real plane. The other thing that's not so good is if I have 1 over some math, then that math can't equal 0, because we can't divide by 0, it blows up to infinity. So these are kind of the two things that we're contending with when we're trying to figure out what the domain of something is. So for this one, we have a root with some math under it, so we'll just take the math and say, this is fine, it just needs to stay greater than or equal to 0, because that's what our domain is going to be. So we bring the 3 over, which says x has to be greater than or equal to negative 3. In interval notation, that would be from negative 3 bracket, because of equals, up to infinity. B, so we have 1 over some math, so that math doesn't get to equal 0. So we'll do x squared minus 1, not so much 0. You can bring this over when you do the root, you got to remember the plus minus, so I'm going to do it as a factor. So x plus 1, x minus 1 doesn't get to be 0. So x can't be either negative 1 or 1. If you do it with the root, here it is, x squared, adding the 1 over. And then here's the only catch, is what I see people do all the time is they do that, and then they write down x equals 1. But what they forgot was the plus or minus that should be when you take a root of both sides. So if you prefer that version, just make sure you get the plus minus on it. Oops, sorry, that was probably loud. C, so C is kind of a combination of these. So this stuff has to be greater than or equal to 0, except it can't equal 0 because it's a denominator. So we're just saying x plus 3 would just be greater than 0 this time, because if it equaled, it would be fine by the root. Square root of 0 is 0, but now you have 1 over 0. That's not okay, because, again, we can't divide by 0. So kicking the 3 over, I get x is greater than negative 3, or in interval notation, just like this, except parenthesis instead of bracket. Okay, then these ones go back and kind of finish out the rest of 1-1. So this is all that f of x function notation and all kinds of evaluating algebraic functions. So do some examples here. So all 4 of these reference this f of x. So x plus 2, so that just means anywhere there's an x, the new x is now x plus 2. So we're just plugging that in wherever there's an x. So this will look like x minus 2, quantity squared, minus 3, x minus 2, minus 28. And then I need to expand that out, so this will go x squared minus 4x plus 4. This is going to be minus 3x plus 6 minus 28. And then collecting terms, x squared minus 4 minus 3 minus 7, and then 10 minus 28, minus 18. For b, it's find x if f of x equals negative 10. So this whole thing is f of x. So basically, if f of x equals negative 10, I can just substitute it right here. So then it's negative 10 equals x squared minus 3x minus 28. Or you could think of it as substituting this piece right there for f of x. Anyhow, they're equal to each other. So I'll bring the 10 over. I have 0 equals x squared minus 3x. Adding 10 makes that 18. And now I can factor. So x minus 6, x plus 3. So x equals 6, or x equals negative 3. F of 0, so that just means evaluate the function at 0. So 0 squared minus 3, 0, minus 28. So if the number's inside, it's the x. This means x equals 0. If the number's f of x equals, that's like y equals. And those often get mixed up on the test. So anyhow, this one would just be the negative 28. And then find x if f of x equals 0. So that means that's the y this time. So we're saying x squared minus 3x minus 28 equals 0. And then that factors, so it's going to be x minus 7, x plus 4 equals 0, and x equals 7, x equals negative 4. Okay, these are still section 1-1. And now it's more the algebraic version rather than the numerical version. So f plus g of x, that just means to add f and g together. So that would be x squared plus 6x plus 8 plus g is x plus 2. And then simplifying, I get 6 and 1 is 7, and 8 and 2 for 10. F minus h, so that means, and this doesn't mean times x, this is just like f of x minus h of x. So the thing with the subtraction, we gotta be a little bit careful. So we have x squared plus 6x plus 8, and then when you go minus, you can't go 3x minus 4. Super important that you get these parentheses right there. Otherwise, your sign's wrong on everything after the first term. Very, very common error. So x squared plus 6x plus 8, and then minus 3x, and it becomes a plus 4. You're welcome to do that in your head, but just showing that the sign distributes. And collecting, I got x squared, 6 minus 3, so that's going to be a plus 3x, 8 plus 4, and 12. G times h, so that just means to FOIL these. So x plus 2, 3x minus 4. So x times x would be 3x squared, x times 4, 2 times 3 would be 6x, 2 times minus 4 for minus 8. And then just collect the terms. And then this last one, f over g, so x squared plus 6x plus 8 over g is x plus 2. Since it's division, we have to check to see if it simplifies. And so if I can factor, which I can, x plus 2, x plus 4 over x plus 2, then I can simplify. So my final on that is x plus 4. Okay, these questions are from 1.3. I'll loop back and grab Piecewise after these. So this is the difference quotient on the test. If you're in my class, I would give you the formula, and then we just have to know what to do with it. So remember with this, we're plugging in the x plus h becomes the new x. So we're substituting x plus h into this function, but then we're substituting that result into this formula. So we're evaluating at x plus h and substituting it into the formula at the same time. So that's going to look like 3x plus h quantity squared minus 4, and then x plus h minus 1. But now that is this piece, and then minus the all-important parenthesis, f of x is this right here, and then that is all over h. So it's kind of a double substitution happening. I'm going to expand a bunch of stuff out, so this is going to go, I think for space I'm going to both, so I'm going to expand this and run the 3 through at the same time. This would be x squared plus 2xh plus h squared, and I'm just going to do the 3 right now. So this will be 3x squared plus 6xh plus 3h squared, and then minus 4x minus 4h minus 1, and then minus 3x squared plus 4x, and then plus 1. So it's like that negative distributing all the way across. And then that's all over h. And let's see. So from there, remember everything in here, everything that was f of x should cancel something earlier. If it isn't, something's gone wrong somewhere and you should go look for it and not keep going because it's not going to turn out. So those cancel, plus 4x minus 4x plus 1 minus 1. So that's kind of the first place you can catch an error. And then I'm going to rewrite what's left, just because it's easy to lose one of these pieces kind of in the handwriting. So 6xh plus 3h squared minus 4h all over h. And we can cancel an h everywhere. And again, that should also happen. So if it doesn't, that's kind of trouble. So this would be 6x, h and h squared would be plus 3h, and right there, 4. Okay, so number 6 is find the average rate of change, f of b minus f of a over b minus a, of this function on that interval. So this is your a, and this is your b. So what we're going to do is evaluate, so a is, let me actually write out what we're going to do. We're going to find, so b is 3, a is negative 2. So this is f of 3 minus f of negative 2 over 3 minus, careful with the signs there, negative 2. I do better, at least for me, if I kind of write that out. So then I'm just going to, this is my f of x, so I'm going to put in 3 and subtract, put in 2, and it'll be over 5. So up top we're going to have 3 squared minus 5 times 3 plus 3, and then minus negative 2 squared minus 5 times negative 2 minus 3, all over 5. And then cleaning that up, I got 9 minus 15 minus 3 minus, keep that in brackets for another second. This will be 4 plus 10 minus 3. And then, let's see, this would be minus 6 minus 9. And then minus 14 minus 3 would be 11 over 5. And that's going to be negative 20 over 5, or negative 4. So my average rate of change is negative 4. And so this is the same idea, except now there's a variable. So it's going to be algebraic rather than just numerical. And so this is my a and this is my b. So that means I'm finding f of t minus f of 2 over t minus 2. So that's going to look like 3t squared minus 5t, and then minus 3 times 2 squared minus 5 times 2. And that's over t minus 2. So this piece is 3t squared minus 5t, And that's going to be minus, let's see, 2 squared is 4 times 3 is 12 minus 10. And so that's going to be, oops, that was all over t minus 2. Sneak that in there. So then that's going to be 3t squared minus 5t. And then that would be a 2 in there, so minus 2 over t minus 2. And then unfortunately we have to see if this cancels, and it will. So I'll do magic method factoring, but you can do whatever you want to get this factored. So I'm doing 3 times negative 2 makes negative 6. And what multiplies negative 6 adds to be negative 5 would be negative 6 and positive 1. Careful not to get the 2 and the 3 there, because they would multiply to a positive 6. So then this would be like 3t minus 6 and 3t plus 1. Divide out the fake 3, and we'll get t minus 2, and then 3t plus 1 over t minus 2. Canceling those. And I have 3t plus 1. Okay, section 1.2, we had piecewise functions, so let me loop back and grab those now. And these are really hard. This is something that once you're really good at graphing, you can kind of get these going fairly easily. But this is kind of the quarter where you really sort of learn all your graphing techniques, and these are tough for most people. So I'm going to think of it as, so we have this x is less than 0, so I'm going to draw this function in orange, and I can only draw it on this side, so orange has to stay over here. And this one is for x is greater than or equal to 0, so I'm going to draw this function in blue, but the blue one has to stay over there. And right there at 0, 0, that's the boundary. It can't, the orange one can't cross over here, the blue one can't cross over there. And also there can only be one solid dot. Everything else would have to be an open dot, otherwise it's not a function. So what negative 2x is, and it looks funky when it's all wrapped up in this stuff, but it's just y equals negative 2x. It's just a line. And so if you're comfortable graphing that using the slope and intercept, that's cool. If not, you can make a little table, and you should go back and get comfortable graphing this by the slope and intercept. The one thing I like about the table is it does sort of emphasize that you're plugging in these points, and you have to pick ones that are less than 0. Nonetheless, I'm picking 0. And I'm just going to write myself a little note that says that's where the hole on the endpoint goes. So I always graph the hole, and it's a line, so I only need one more point. So if I do negative 1, negative 1 times negative 2 will be a 2. And so this one's going to look like this, and then slope of over 1 up 2. And then this one, y equals negative x minus 3. And so this one, 0, 0, and that one's going to be a solid dot. And when x is 0, y would be negative 3. You could just also use the intercept. And slope of negative 1, so it's going to over 1 down 1, but if I want to put in one more point, then I get negative 4. So at 0, negative 3, there's a solid dot, and then it's just going to over 1 down 1, because that's slope. And then I think, yeah, find the domain and range. So that can also be really tricky on these. Domain is not tricky at all. Domain is sitting right here. It could be less than 0, equals 0, and greater than 0. So your domain's all real numbers, or negative infinity to infinity. The range on these is tough. And so you have to think low to high. And so it's going to go from negative infinity. It's going to come up, and it's going to come up and be at negative 3. So we have a solid point there, so we have to include that one. And then there's this gap, and so we skip that with a union, and it picks back up at 0 and goes to infinity. And that one has to be a parenthesis because that one's a hole. These are really hard to see. A couple of things you can do that sometimes help, and it just sort of depends on the person, how your brain works. For some people, if they turn the graph 90 degrees, they can go from negative infinity to negative 3 very comfortably then, and from 0 to infinity. If you just kind of treat it like domain turned sideways, for a lot of people that really helps. That's probably the best one. For some people, if you think of a flashlight shining on this, any place it casts shadow, which would be all up in here and all down in here, right? If I had light shining on it, anywhere there's shadow, that's going to be your range. So sometimes one of those two sort of helps people see what's going on with that. So for number 9, we have 3 functions going on. And so this is x is less than negative 2, between the 2's greater than 2. So we should have graph everywhere because our domain is all real numbers. So I'll do this first one in, I think it's magenta. So we got y equals x plus 5, but only good for x is less than or equal to negative 2. And so for me, graphing that with, because I'm used to going, okay, x is 5 over 1 up 1. Now I'm drawing my line in the wrong spot. I can only do that less than negative 2. And so I'll often just grab that endpoint of nothing else and toss it in just to kind of get myself orientated, and then I can use the slope from there. We could also grab just one more point, and then we'd be all good. So negative 3 plus 5 would be a 2. And this one is a solid dot. So let's see, when x is negative 2, y is 3. And when x is negative 3, y is 2. So we're getting something kind of like that. This one, so this is one where I wouldn't use a table at all. And so when we first met these, we kind of had to use a table because we didn't have transformations. But now we've done section 1.5, you should be able to graph that hopefully really easily. If not, you need to go study transformations because there's like 3 of them on the exam. But with this should just be x squared. It's our u shape over 1 up 1 over 1 up 3, shifted down 2, and I have to draw it only between negative 2 and 2. So if I just come over and go start at negative 2, it's just those 5 inner points. We've drawn a whole bunch now. And so this over 1 up 3, and these don't have equals, so I'm going to be careful to make those ones holes. So there and there. And then lastly I have 3. So what 3 is, it also doesn't need a table. Y equals 3, that's going to be a horizontal line through y equals 3. But only good up to and including 2. So we're going to start at 2 and go that way. A good way to think of, and so this is what the graph would look like. Actually, let me finish domain and range so I don't forget that. And then I want to talk about this just a tiny bit more. So domain we already decided was negative infinity to infinity. And then range is low point. Careful not to fall for that one. This one goes forever down. So that's going to be from negative infinity. And then this magenta one is solid, right? So it's going to come all the way up to 3. So I don't have to worry about these gaps here because it's included right here, and that 3 is already included also. So just up to 3. So the thing I wanted to say about these, not a bad thing to do at the start, is to take x is less than or equal to negative 2. So that's a kind of a vertical line right here. And I don't want to give the impression that this is an asymptote, because it is not. But it can kind of help, like, just mentally as you're trying to, like, work these things out. And then the other one's at 2. To kind of sketch those in and go, okay, this one has to stay over here, and give yourself kind of a physical boundary. This one has to stay in here, and the green one has to be over on this side. The graphs can't cross those, and then they have to go all the way up to them. But sometimes if you give yourself like what you're aiming for, it sort of helps you settle into getting it graphed correctly. Okay, and then last example for these. So this one would be y equals negative x plus 1. And I did 2's again. So this time I'm going to go ahead and draw that. So again, not an asymptote, just sort of a visual aid for trying to keep ourselves where we're supposed to be. So then that says this one has to be over here, right? So I could do negative 2, negative 3, x, y, x is negative 2, x is negative 3. So negative of negative 2 would be 2 plus 1 is 3, and that's going to make this one come out to 4. So negative 2, we have 3, and that is solid. And then at negative 3, I have 4. And then it's just going to follow up like that. In the middle, I have absolute value x minus 2. So that's our V shape shifted down 2. And so we'll just do a hole here and a hole here. And again, this is something that when we first saw these, we would have to do a table, but now that we have transformations, much easier to do that way. And then lastly, I'm going to draw y equals 5 from 2 on. So 5 is right there, solid dot, and then just heading on to infinity. So for this one, domain and range. Domain is all real numbers, and then the range is from negative 2, that's our low, up to but not including 0, and then the blue one picks up at 3 and goes to infinity, which includes the 5. Okay, that brings us to section 1.4, which was composite functions. So remember, there's 2 notations, and so this one written the other way is f composite g of x. So either one of those means the same thing. I guess I should have a 2 right there since this is 2. So this means, I kind of like this one better. So we're going to find g of 2 first because that's our inside function. So g of 2 is just 2 plus 3, or g of 2 equals 5. Once I know that, I just put that into the outside function, and I find f of 5. Because g of 2 is 5, I'm substituting 5 right there. And then that's going to be this one. So 5 squared minus 2 times 5 plus 4. 25 minus 10 plus 4. And so that'd be 15 plus 4 is 19. G of f of negative 2. So now f of negative 2 is the inside function. And that's going to go negative 2 squared times negative 2 plus 4. So that is 4 plus 4 plus 4. So f of negative 2 is 12. And then 12 goes into the outside function, so I'm finding g of 12. So that's 12 plus 3, or 15. 12. So f of x equals x minus 3, g of x equals root 5 minus x. And we're finding the composite of these 2 functions and then the domain of the composite. So with this one, we're going to go f of g of x. That means we're finding f of g of x, so we can think of it as f of 5 minus x, because that is g of x. So then that's going to look like root, because that's going in for this x right here, 5 minus x, and then the minus 3. So that's this substituted in for this x. The domain on that, the minus 3 thing isn't a problem, but the 5 minus x is. So for that, we just got to make sure that stays greater than or equal to 0. So I bring my 5 over. Minus x is greater than or equal to negative 5. But then when I multiply both sides by negative 1, I have to remember to flip the direction of the inequality. And so my domain will be from negative infinity up to and including 5. Okay, this one's the same directions, but considerably harder because of the rationals. So f of g of x is what we're trying to find. So that means g is going to be substituted in for f. So that's 1 over x plus 5. So there's that substitution, minus 4. And I don't want to have a fraction in my fraction, so I'm going to multiply top and bottom by x plus 5. And if it helps, you can think of this as over 1, and that's going to help you maybe see the canceling on that first piece. So the numerator is going to go just 1 times x plus 5, so that's x plus 5. And then here it's going to be x plus 5 over x plus 5, so that's just canceling, leaving me that 1. And then minus 4, this also multiplies that. So it's like this is kind of distributing. And so it's minus 4 x plus 5. And then careful to not cancel there because we have to combine first. So that's going to be x plus 5. And then 1 minus 4x, and then that's minus 20. So that is minus 4x minus 19. Oops, I didn't really leave myself enough room. Let me scratch that. X plus 5 over minus 4x minus 19. So that's my f of g of x. Didn't write so good that time. To find the domain, there's 2 places we need to look, and one is right here before we simplify. Right there, x cannot equal negative 5. And then the other one is right here after we simplify, because then this can't equal 0. And so I'll just bring that over here, and I got negative 4x minus 19 doesn't get to be 0. And so then negative 4x doesn't get to be 19, and x isn't negative 19 fourths. So there's one piece, and there's the other piece. And I'm perfectly happy with that. You do not have to write out the interval notation on the test. If you just tell me the 2 bad numbers, that totally gets it done. This one's the same thing, just because these are hard. The numbers come out a little bit nicer on this one. So this one is find f composite g, so it's the same thing, just different directions. Or different form of the directions. So f of g would be, this is going in for x, so that is 2 over 5x minus 3 minus 1. And right there, there's our first piece for our domain. X cannot be 3. And then if I simplify, I'm going to do x minus 3 and x minus 3. So here that would just cancel. Actually, numerator first, x minus 3. And then here these would cancel, leaving just the 5. And then minus 1 times x minus 3. And I just need to clean that up a little bit. So it's going to be 2x minus 6, and then 5 minus x minus minus plus 3. And then that's going to go 2x minus 6, and then negative x plus 8. And this would be, if I set that equal to 0, and I add the x over, I get 8 is x, or can't be x. And so you can also just look at it and go, you'd put in a positive 8, so that negative 8 plus 8 would make 0. So those are our 2 bad numbers in our domain. And again, that totally counts as an answer for the exam, for me at least. Okay, so for 15, this is now section 1.7. So again, I'm skipping over 1.5 for a second just to kind of finish out all the function notation stuff, and then I'll do all the graphing together. So let f of x equal this, find f inverse x. So remember our steps, the first thing we do is we swap x and y. So that's going to be x 10 plus cube root of y, and then we just resolve for y because this is supposed to be a function of x, which means the y would be by itself. So the first thing I do is subtract that 10 over, get that out of the way. And then that's going to get us x minus 10 is equal to cube root y. And then I will cube both sides to undo the cube root. And that's pretty much it. So we end up with x minus 10 cubed equals y, which is our f inverse x. For this one, so same idea. We'll swap x's and y's. So this is going to be x equals 3 x. Oops, shoot. I always do that. X equals 3y to the 7th minus 5. So I'll add that 5 over. And we get x plus 5 equals 3y to the 7th. And then we divide the 3. And so then, and I think I'll write it the other direction just because it looks nicer. And then from there, we'll just take the 7th root to undo the 7th power. So we'll 7th root both sides. And we get y, which is the inverse now. 7 through x plus 5 over 3. Same thing, swap x's and y's. So it'll be 2 plus 5y minus 4. And then we're supposed to find the inverse. So I will subtract the 2 over. X minus 2 equals root 5y minus 4. And then I will square both sides to undo the root. So now I have x minus 2 quantity squared equals 5y minus 4. And then I'll add the 4 over. So x minus 2 squared plus 4 equals 5y. And then we'll just divide the 5 on both sides. And then that will equal the inverse. And then this last one, for 1.7, this one's a little bit sneaky because of we're going to have 2 y's to solve for. So this would look like x equals y plus 3 over y minus 4. And so the first thing I would do is clear the fraction. So I'm going to do y minus 4 on both sides. So these cancel, and then x times y, and then minus 4x equals y plus 3. And then I want to get the terms with y on one side and everything else to the other. So I'm going to subtract this y over. I'm going to have x, y, minus y, and I'm going to add the 4x over. So plus 4x plus 3. And then the trick right here is just to factor the y out front. So y, x minus 1, and you kind of double check yourself, equals 4x plus 3. And I'll divide this over. So that leaves me y equals 4x plus 3 over x minus 1. And that's our one more inverse question. So this one is, given this function, find the inverse, sketch a graph of the function and its inverse. So we'll do x equals 3y plus 7, and then I'll solve for y. So x minus 7 equals 3y, and then divide both sides by 3. X minus 7 over 3 equals y. And so that's still a linear equation, but that one is really not that cool looking to graph. So if I do a table down here for my original f of x up here. So if x is 0, y is 7. If x is 1, that's off my graph, so I'll do negative 1. But negative 2, that's good, because that'd be negative 6 plus 7 makes 1. The far enough part I can maybe draw it. And then, so then the deal is, for this one that's all terrible that I don't want to graph, which is my inverse, I can just, reverse the points, and then not have to work too hard to get these. And we can use them as a check. 7 minus 7, right, that would be 0 divided by 3 would make 0. If x was 1, 1 minus 7 would be negative 6 over 3, and it does make negative 2. So it builds in a little check also. So for the inverse, let's see, when x is 7, y is 0. And when x is 1, y is negative 2. So that looks about like that, I guess. And then for this one, when x is 0, y is 7. And when x is negative 2, y is 1. So about there. And then this has that symmetry that we kind of expect out of a function and its inverse. If we fold this across the line, y equals x, then it sits right atop itself. Okay, so that brings us to transformations, and just kind of a reminder of them all. When we add or subtract on the outside, that's where our graph is going to shift up or down. So it's a vertical shifts. Horizontal shifts are when we add or subtract on the inside, and this is the one that's backwards intuitive. If we go plus, it goes left. If we go minus, it goes right. It makes sense when you plug points in, but again, it's easy to get kind of crossed up on that. Stretches and compressions. So if we have a number out front and the number is, actually that should be greater than 1 right there, sorry. It's greater than 1. Then this would be a vertical stretch. If it's between 0 and 1, it's going to be a compression. And then if the number's on the inside of the function, and these I'm not sure I did anything with in the review, I'll have to peek, but this is very much a trig thing. You do lots of this in trig, not so much with the more algebraic functions. They just don't lend themselves to that so much. But that's where we got the horizontal stretch, and this should be another 1 right there. Sorry about that. So stretch if it's between 0 and 1, and then compression for greater than 1. These ones we do see reflections about the x-axis. So if we have a negative in front, that's where it flips over x. And if we have a negative on the inside of a root, that's where it flips over y. So let's look at some examples with that. Okay, so then as we encounter these different functions, I'm going to do the parent function just once for each one to kind of remind you what they are. So this has like pretty much everything going on that it could. But at its core, it's an x squared right there. And so that's our over 1 up 1 over 1 up 3, over 1 up 1 over 1 up 3. At least that's how I remember it. So that's our parent function. And then all kinds of stuff happened to this one. Let's see, it's going to go up 2, it's going to go left 3, it's going to reflect x, and it's going to get stretched by 2. So, okay, let's get the up and left part. So it's going to go up 2 and left 3. Up 2, left 1, 2, 3, so that's right there. So that's the new vertex, and now it's going to open down, and instead of going over 1, up 1, it's going to go over 1, down 2. And there's your stretch by a factor of 2. The next one, if you want to be fancy, would be 6 below that. You don't have to be that fancy. I'm probably going to miscount it. There we go. But it would look basically like that. So this one is absolute value x, and so remember that's the V-shaped one. So it just kind of does over 1, up 1 forever on both sides. And this one has been, this is going to go down, this is going to go right, and then it's going to flatten out by a factor of 1/2. So let's get the right and the down. So right 3, down 4. And then I kind of think of this as a slope. You know, when it's just plain absolute value x, it's over 1, up 1. So this is going to be over 2, up 1. And then on this side, it's negative slope, but it's still kind of over 2, up 1, if that makes sense. Just to kind of conceptualize how to draw that. And we get something like that. Okay, the stretches on the roots are kind of hard, and so I'm going to do that serve as its own separate step and just kind of make a parent function for it. So my plain old root is over 1, up 1, over 1, up 3, or over 3, up 1. So it would look kind of like that. And so if I just wanted to do y equals 3 root x, just to get the hard part of the graph done, and then I can use that to kind of help me with the transformations and get it shifted, but it's nice to do this next to the axis. It's basically just going to triple the outputs. So if x is 0, this is still 0, but now when I put in 1, I don't get 1, I get 3 times 1, or 3 times as much. When I put in 4, I used to get 2, now I get 3 times that, or 6. And so we get that graph right there. And then I just got to take that one and move it down 4, and that would be left 2. So down 4 and left 2, first point, down 1, 2, 3, 4, and left 2, and then down 4 and left 2. And then just kind of connect the dots in a smooth curve, and then there's our transformed one. So another root x this time. But this one is flipped, it has both flips. So the negative in front would flip it down, the negative on the inside would flip it across, and the 2 on the outside is going to raise it up. So it's like, it was, you know, the original is just kind of like that, and then the negative in front does that, and the negative on the inside folds it over there. And then that plus 2 is going to take that and shift it up. So now it's starting from right here, over 1, down 1, and over 3, down 1. There's the root. Okay, and then last is, let's see, the exponentials were 4, 2, the logs were 4, 4. If you have not checked out the graphing supplement on this, and actually if you haven't checked out the graphing supplement on 1.5 and Piecewise, you definitely should, because they're exactly how you would see the questions on the test versus the homework, where I'm kind of limited to whatever it is they gave you for questions on the computer. So what you see in the graphing supplements, what you see here is how the test is going to look. So remember with these ones, we want to kind of do a parent function just based on whatever the base is. So y equals 5 to the x, and so remember we just do -1, 0, 1, and then 1/5, 1, and 5, and after that we'll use transformations for whatever we're given. So our parent function would be basically like this. And it's always going to come out 1 over the base, 1 in the base. So they're pretty easy to get the parent function. And then this is, not sure if it's big enough for you to see, but it's x plus 4 in the exponent. So that plus 4 is going to go left 4, and then this is going to go down 2. I never start with the hard point. I always start on the easy one, just to make it easier to count. So left 4 and down 2. This would be left 4 and down 2. And then I just kind of look at, I use this as a reference and go, so from here it's going to go over and down a little bit. And I get that. So it asks for a couple other things that people sometimes forget to say. It asks for the horizontal asymptote, and I would encourage you to draw it in, because then you are certain you don't draw your graph past it and it can't go past there. So in this case that is y equals -2. And then domain and range. So domain for an exponential is all real. And then the range is going to be from wherever that asymptote is, either up or down to infinity, depending on the orientation of the graph. So for this one, it's going to be -2 and then up to infinity. Number 25 is an example of a log. So for that, we're going to have basically y equals log base 4 of x. So that's the same thing as 4. Usually we write the y on this side and it's easier. 4 to the y equals x. Or you can just think of this table and it's inverse, so just reverse the points. And it's going to be -1, 0, 1, and then 1/4 this time, 1 and 4. And so then when you draw that in as a parent function, just kind of a reference. So again, I don't usually start with a hard point, so I'll go the 1, 0, and then 4, 1, and then right there. So 1/4 and then -1. So there's my parent function. And then this one is going to have, it's going to be up 4, it's going to be left 3, and then this is going to reflect it down. So if I wanted to draw just the reflected down part, it would be just like that. And then I can move that left 4 and up 4, left 3 and up 4. So from right here, left 3 and up 4, left 3 and up 4. And then this is where it's nice to draw in the asymptote. So it's going to be, since this is shifting left 3, so is the asymptote. And so it'll be right there. And so vertical asymptote is at x equals -3. Make sure to distinguish what you're talking about, so don't just write down -2, because the asymptote isn't -2, it's y equals -2. -2 is just a number, -2. Likewise, this is distinguishing it as a vertical line. And then domain range, sorry. So this is going to go -3 to infinity, and then the range for these is all real numbers. I think there's a little talking to myself in the kitchen fatigue setting in here. And we got 2 more, and that's it. Okay, so another log. So this one, let's see if we can just do the table straight away. So xy. So it's going to go -1, 0, 1, and then since it's a base 3, it's going to be 1/3, 1, and 3. And we'll get the parent function drawn in there. So 1, 0 right there, 3, 1 right there, and then 1/3, -1. And it should kind of look something like that. And then this one is going to be up 3, and that has a negative on the inside, so it's going to reflect across this way. So that would be right here, here, and here. And I'll just take that and shift it all up 3. So take this point up 3, this point up 3, and that point up 3. Vertical asymptote stays at x equals 0. Domain is from -infinity to 0 and not included because that's the asymptote. And the range of this is all real numbers. And last one, so our basic for this would be x, y, -1, 0, 1. It's a base 4, so 1/4, 1, and 4. So that would be 0, 1, and then 1, 4, and then 1/4 right there. And this one is going to be reflected down, so I'll go ahead and draw that piece. And then now that I have that, and then it's also reflected across. So I'll go ahead and draw that piece. So there's, I don't know if you can see it up in there, but there's a little negative x in the exponent. So that's going to reflect it this way. And then finally, that's all going to get moved down 3. So I have points here, here, and here, so I'll just scoot all those down 3 units. Actually, let me change colors. There, down 3, and down 3. And since the graph shifted down 3, that puts my asymptote at -3. So that is y equals -3. And then my domain on these ones is all real. And my range is going to go from -infinity up to -3. And that wraps up the exam 1 review.